Hi and welcome to another video by KOJRO. This is an of these interlude videos where between other videos, and I will try to set a few things wrong about capacitors and ripple and power supplies. So, and by the way, this title is an obvious wordplay of Patricia Highsmith's book about the talented Mr. Ripley. I thought that was a very nice pun. Hope you agree. But this is not what this short video is going to be about. And what you can see here on the screen, you will see that we have some no, wait a minute. I have some drawings about different things that is, rectifier or power supply-ish. And I'm going to explain some of these terms. And I'm also trying to, explain some of the things more in depth than I will be able to in my other videos. And hopefully I will check what kind of audience I will reach with this video here. So we switched off the video like so, and I go to the next page, and here you can see what we are talking about. I will switch on the video again. This is a sine wave, and I once had a teacher at the university that was able to draw this flawlessly with a special movement in his knees when he was using the blackboard. But this is an approximation of a sine wave, and we do have some terms here. The V top or V point to point is this distance here from top to bottom, and it's from the highest top to the deepest valley of a sine curve. And we are assuming that the sine curve is then swinging about a neutral point where you have the same landmass here as you have here. And that is what we call a sine wave. We normally draw it that it starts with 0 and it's a full cycle that goes like so, and the frequency is determined with the time it takes for it to swing top up and top bottom. So the frequency is the inverse of this time period. So that's the basics about a sine wave. I'm going to move the video down so. This is a full bridge rectifier. As you can see, it exploits all of the sine wave, and this works like when you have a positive swing, it will conduct like so, and when you have a negative swing, it will conduct like so. So you are turning this as a positive signal when we take it out on the bottom. But what we are seeing down here is, I can just take it away like this. This actually just let the positive wave pass through, and when this comes down to 0, it just blocks the other direction. To make this, to be able to have a circuit, you do have to have some resistance or something here that will actually make this diode to make a circuit. But as you can see, here you are cutting away this half of the sine wave. So you are only getting half your transformer's worth of power on the output. This is still used on a lot of high frequency stuff, and in switch mode power supplies, this is very often the case that you have this kind of rectifier on the high frequency output. So that's the basic of rectifiers. We are trying to make this sine wave goes like so to a signal that only has the positive part of the sine wave to make a DC current. And this is called unsmoothed DC current, even though it's not alternate, and that is because it's swinging from 0 to V top down up here. So we are calling this a DC signal, but it's not a regulated and it's not a smoothed DC signal. Here we can see what we are measuring when we are measuring with a multimeter. And this is the general formula to the area that is underneath here. That will be the effective value. It's how much power you can make this sine wave to dissipate in a resistor. So when you are measuring here, the total value of the power that you can get out of this is determined by the square that is filled with something. And as you can see here, I've tried to illustrate how this works. When you are taking the mean value of this, you take the area that is up here and you try to fill it in the blanks down here. And when all the voltage or power or potential that is going here is put down to here, then you will have the effective value or RMS, real metric value of your voltage. So you do have a V top here. Let's say that is 10 volts. Then you will have about 7.7 volt as this point here. 0.7, like so. And this is the general formula, but a sine wave is a special circumstance of this. So for a sine wave, it's 1 over the square root of 2, that is 0.707, times the voltage top. So that means that our effective value here is about 7 volt when you have a 10 volt top here. And that is what you are measuring with a multimeter when you are measuring on this kind of signal. And also it will be what you are measuring if you are measuring on a sine wave that is going like so. Because this is the total area that is filled with something here. And here you can see the same with the half wave or just single diode rectifier. You can see here that you need a much larger area here to fill up the bottoms because you don't have this other part of the sine wave up here that will help to fill the bottom. So here you only have half the voltage measured as a real metric value. And that is determined by the square root of 2 times 2, like so. Or you can take the value and just divide it with 2 afterwards. So if you had 10 volt here, you have about 7 here, and that means that you have here it's 3.5 volt. So that is the basics when you have a rectified signal and what you are measuring with your multimeter, and be it a true RMS or something, it doesn't matter with a sine wave, because every El Cheapo multimeter is able to get this right with a sine wave at 50 or 100 hertz. The problem is when you have more advanced waveforms, then it does matter that you have a real RMS multimeter, because if you have this kind of curve, it's not 0.0 that defines what you will have here. Actually, in perfect, I will take out some of this. It might be relevant to just put this right. If you do have something that goes like so, try to make this like a perfect triangle, and this should of course be in the middle, then you will just have these waves that is up here, and this is less than a sine wave. So we will get less RMS value than if you have a sine wave. And if you have something that looks like so, and you have a perfect square. When I say a perfect square, you need to have some imagination. You can't just take my word for this. Like so. Then you will see that the mean value will be V top half. Because when you rectify this, you will have this filled in here. So what you will be measuring with an RMS multimeter, if you have a perfect square, is that you will have V top parted by 2. So lots of nonsense in this, but this is basically how you get from a top value to your RMS or effective value. And with a sine wave, RMS and effective value is always the same, even with the El Cheapo multimeter. Yeah, and before you come knocking on my door and tell me that I'm full of shit, I did get this wrong. It's of course the V top to top voltage parted by 2, not VT parted by 2. So it's VT, not VT parted by 2. That is actually the actual voltage you will measure on a perfect square that is centering around 0. And here is what happens when you put a smoothing capacitor on this. Here you have your full bridge rectifier and you have a smoothing capacitor here. You still have your signal here that is rectified. This down here is your value from the sine wave. But you will charge the capacitor, and this capacitor will hold its charge and discharge slowly, and it will be recharged again when you get a positive value here. Of course, you do have to have some kind of load here to discharge your capacitor. So not throwing on a load here, what am I trying to pull? And it means that you sort of get this for free when it comes to voltage wise, because here you will have charging of the capacitor, even though the capacitor will in theory hold the V top value here. So when you are charging the capacitor, you will have a voltage that will stay higher than your RMS value. And that means if you take this and point the opposite way, if you have your V RMS value and you measure that to be 7 volt, then what you will get if you put on a smoothing cap on a sine wave signal like this is that you take and multiply it with the square of 2, that is 1.41421335, or you can just say that this is the square of 2. So that means that you will have about 10 volt. Of course, we will lose some in the diodes and so on, but you get my gist here, that when you are measuring on this signal, you will get more voltage than we had earlier, because this smoothing cap is trying to keep status quo on this. So when this is taking charge, it will charge, and it will slowly discharge into the load. And of course, the size of the capacitor and the load will determine how much the voltage will sink before it gets a new boost up in this area here again. So that was the charging of a capacitor, discharging, and the ripple effect, explained very simple. But how does this work? And we are going to look more into a capacitor. Here you have a really simple circuit, and we can think that this switch, each time you switch off this sine wave here, or rectified sine wave, each time you are putting this in, you will charge the capacitor, and when you open the switch, the capacitor will discharge into the resistor that is here. And we do have a formula here, and this strange looking T here is what's called a tau, at least that's what we called it back in school. And this is the time constant. And the time constant, this is a definition that is often used in electronics, and that is that tau, or big T marked or something, it's called a lot of things, but I learned that it should be called a tau after the Greek letter. This is the time it takes a capacitor to charge 63% or discharge 36%. And that is the amount of time when you have the charge curve, that is the green one. If we have 10 volt here, then is when this charge has reached 6.3 volt, then the time that takes is 1 tau. And this is also used in cases where you have filters and other stuff. They also use about the same values. And you can see here the discharging is also determined the same, and the charge curve and the discharge curve for a capacitor is about the same. There are some differences, but we are not going into them here. And this is what keeps, if we draw this down here, when you have this, oh, it was smoothing them out for me. This here is the, I will do it like so, and I will move outside the picture and I will change the color. This time here is what you actually get to charge the capacitor for the first time, and it will charge until it comes up there. And then, strange for me making these color choices, they have nothing to do with the rest of the figure, but go figure. And this is the discharging. So here it's charging. When it reaches the top, it's if you open the switch and it starts discharging here. So this is what's called the ripple voltage. And this is how capacitor works. They are used a lot of these things, but in reality, you have a lot of uses for capacitors, and they are often named for what you use them for. You have decoupling capacitors, you have coupling capacitors, and you have filter capacitors, and you have reservoir or smoothing capacitors. When you are using this to smooth out a signal from a power supply like this, it's a smoothing cap. And it's also, of course, a reservoir cap, because the circuit is drawing from this reservoir when you don't have any other source of power in your system. Yeah, but why don't use a battery? And that is a very good question indeed. And today we have something that's called a supercapacitor that have a discharge, that holds a charge that can in some way be compared to a battery. We are talking about capacitors with several farads in capacity. But still, a battery is able to hold a charge longer than a capacitor. And when you have really fast charging time on a capacitor and fast discharging time, a battery's main function is to keep the load happy for a long time. But you can still charge a battery with a sine wave. And in fact, if you take your old, really old car lead acid battery charger, it actually contains a rectifier, either a bridge or normal, and it doesn't have a smoothing capacitor. So a lead acid battery is actually charged by this charge here. And if you are measuring on a battery charger, you actually are measuring the voltage that you have here, that is the RMS value, but the peak value will be higher than your nominal charge. And that is actually good for a lead acid battery, because this over voltage here will actually excite the cell and the electrolytes. And it's really the mean value here that is the charge that goes into the battery, but this keeps the battery from getting stale in that you have some over voltage. You are pulsing this. And when you are taking an old lead acid battery and you are reforming it, one of the ways to reform it is actually to put a voltage that a high pulse with several voltage, something like this. You put on a 12-volt battery where you have 12 volt here. You actually try to put maybe twice the voltage in this to reform the battery in some way. So talking about a tau on a battery makes no real sense. A real battery has a much higher internal resistance, and the capacitance or capacity is larger, so you will have a very long discharge time. For a car battery with 60 ampere hours, ideally you can charge this with 1 amp for 60 hours or 60 amps for 1 hour. So it's a totally different function, but it's both devices that actually can hold a charge. And this is showing about the same when you are missing this part of the sine wave, when you are doing single rectifying like this. And of course here you do have a shorter charging period for the capacitor. It's always able just to charge when this is going upwards, and it will discharge on anything between. So if you want to have a low ripple here, you need a much larger capacitor for this. And here you can see this is discharging about 50%. That means the tau for this capacitor is probably this distance here. This is the tau, where it reaches, maybe it was here about, but this is where it reaches 63% of the top voltage. So with a single rectifier like this, where you are not having a bridge rectifier, you will lose a lot of your potential for charging the capacitor, and you will get a larger ripple voltage. A ripple voltage is from the lowest value to the highest point on this. So that is with a rectifying, and you can actually say here that the maximum ripple voltage that you will have from this is the DC load and divided by 2 times F times C. So frequency times the capacitor. And if you had this, if you had this too, you can take away this. Then it will be the DC current on the F times C, because this will have a much lower, much less time to do the discharge with the same load. That was right, yes. And next picture, this is just telling us the same. I've tried to illustrate this with what kind of voltage you are getting out of this. You have this initial charge time here, and it will keep like so. So the red line here, or of course I'm now making it blue, is the voltage that you will have out of this. So will look something like this. You will have a small ripple. This actually should be more linear. Sorry, that didn't. It should resemble this totally. When you see it, this blue line. So this is what you will see when you look at just the rectified signal on a scope. Rectified with the smoothing capacitor, I mean, and a load. And if you put on a higher capacitor, or you are having less load, then you will have less ripple. Remember, the ripple was E DC, and that is just mean that you have the effective current or power that is dissipated in the circuit, and it F times C. So you can either increase the frequency so that you have shorter time for this to discharge, or you can change the size of the capacitor so that it will be larger. And if you have a larger capacitor, it will be illustrated. It's silly to show these colors. I will just show the green one. This is what we see here. This is the discharge we will get with a larger capacitor. And if we had the same with a higher frequency, like so, that was very bad drawing. If you have a very high frequency here, you will get less time to discharge. But anyway, we will have some ripple voltage. And this is also why you can't say to have normal ripple voltage on a switch mode power supply, because a switch mode power supply, it's switching the output maybe from 80 to 500 kilohertz. And that beats this 100 hertz or 50 hertz if you just have single phase, not single phase, that's wrong to say, just single diode rectifying. So increasing the frequency is not an option when we are dealing with transformers and main voltage. That is always a source of 50 hertz, and when you are turning the signal so it repeats itself, if in just half the time you have 100 hertz. And of course, for you Yankees out there, it's 60 hertz and 120, but it really doesn't matter. But it means that your time for discharging capacitors is lower, so you will be able to get a lower ripple with the same other constants. Yeah, and of course it's the same. This is showing what will happen when you lower the frequency, because this is the 50 hertz. Like so. And of course the same applies to here. If I put on a larger capacitor, it will discharge less. But you do have a much larger area to fill up and a much more time gap to fill and to strain the power or the charge that is in your capacitor. But what does it mean? In the amplifier build that I'm trying to put together here, I actually have 4 6800 microfarad capacitors. They are some El Cheapo Chinese stuff. We have tested that they actually works, but how good and do they keep 6800 microfarads? I have not tested them yet. I can test them. I can load them down with a known resistor and measure the time it takes for them to discharge to 63%. Then I can use the formula for the tau and just calculate how much capacity they have. And to say what the maximum ripple voltage will be, it's not a given formula for this, because it depends on the design and it depends on other stuff. But when we have a symmetrical power supply, like we have here, you can actually compare it to that you have something like this, because the rectifier bridge is giving you something that looks a lot like this. So you have one negative and you have one positive part of this equation. And you do have a 120 volt amp transformer, and the reason why it's called volt ampere and not watt is because you have some power correction factor on this transformer because it's an inductive load. But let's not get into that. For all our purposes, it's a 120 VI transformer, and it's also said that you can load this down with 120 volt amps, and it will get so and so hot, and it will last for so and so long. You will be able to get more out of this transformer, but then the voltage will perform lower than you have because of the internal resistance in the copper wires. And if we take some presumptions here, and of course I said already, this is just in some part guesswork. We have 120 watts, that is the maximum the transformer can deliver, and we are going to deliver this in an 8 ohm speaker. Again, a huge simplifying, because an 8 ohm speaker is not 8 ohm over the whole frequency area. But let's just say that we have some very, very bassy music, and it is performing 8 ohm in the lower frequency range, and you do have an amplifier that is able to deliver what we ask it to. And then we can say that the current that is supplied here is 120 watts divided into 8 ohms. And this is just the normal formula for current. It's like so. Yeah, you just take your power here. We can just see that this is the watt, and we put it over the ohms, like so. And then we get 3.85. 3.85 is some current. And if we take to put that into our voltage ripple formula, and we can say, if you take this ripple on this side and this side, and say that they are not occurring at the same time. So you can look at these two ways. You can take all the force capacitors, or you can take half of them. I have chosen here now for the simplicity of things, and that you can get the gist of how we are doing this. We take the current, the DC current, and you take the frequency, that is 100 Hertz. It's a dual bridge rectified 50 Hertz signal, and you just multiply it with the capacitance, and that is 6800 times 2. And it's micro, so it's in the -6 exponential, and that means that you are just moving the comma this way, and you time it with 100, and you get 1.36. So the total ripple on this will be 2.8 volt, and that is actually quite a bit. But of course, this is the maximum circumstances, and I don't think we will get this much power out of the circuit. And if you don't get this much power, then the ripple will be less. But if we have idle circumstances where we are delivering all our power into the amplifier, and that everything is delivering as it should, then we will get this. But you must remember that this amplifier and stuff, it's also not 100% efficient, but everything will be drawn from the power supply. So when you are loading this fully, you will get this ripple on this. So larger capacitor, yes please. And in my other amplifiers, I do have, yeah, I think 10,000 and 15,000 microfarads times 4. It's not something that I would have screamed about, but of course, When you have this part of the signal, let's say that this is I will change color, say yellow one. You can just draw on this. If you take this part of the signal and say that this is the first time we are charging the capacitor, and this on the negative side when you are turning things on. If this is the first time you are loading this, the capacitor will act about as a dead short on the output, and you will blow the fuse. So there is quite the large current that is going when you are charging this capacitor. You remember the charging curve for a capacitor, it's quite steep. And you are not having much resistance here. The capacitor is coupled just after the windings and the copper cable that was in the windings on the transformer. So here you get the gist of the Ripple. You will be the judge if I am the talented Mr. Ripple in this, or if I'm just some bogus charlatan that is giving you some nonsense about this. But this is actually my old school curriculum that I just put into action. So hope you enjoyed the contents. Please watch some of my other videos. And if you want some more nonsense in-depth videos about a slightly moronic or nerdic theme like this, just leave a comment below. And I hope you don't lose many subscribers on this video. I think the last video is actually the ones that has given me most subscribers. Quite a while, I get 4. The last 2 videos I actually lost 2 and gained 1. So it's going downwards. But hope to see you in my next video. Please hit like and subscribe, watch some of my other contents, and the amplifier series will continue in a bit. Thanks for watching.